We are capital rich but build poor.
It's the paradox of the decade. We solved the funding problem, which, everyone thought was the hard part.
Right.
But it turns out money doesn't dig trenches. Money doesn't hang high voltage wire by itself.
So in this deep dive, we're unpacking a new report that proposes a solution that isn't just throw more money at it. It's about a convergence of two things that honestly sound like they're straight out of science fiction.
They really do. We're talking about high voltage, direct current technology, HVDC, and, well, an army of robots.
And we should be clear about what we mean by robots here. This isn't just an automated arm in a car factory.
No, not at all. We are talking about autonomous trenchers, exoskeletons for line workers, drones that can work on live wires. It's a different level of automation.
The report calls it a force multiplier strategy. But before we get to all the cool robot stuff, and we are definitely getting there, we have to set the stakes. Because the numbers in this report about our energy gap, they are genuinely terrifying.
They're stark. To hit our decarbonization goals, and maybe more urgently, just to keep the lights on for this AI boom and all the reshoring, the U.S. grid needs to expand by about 2.4 to 3.5 times its current size by 2050.
Wow. That's like rebuilding the entire grid we have now, twice over.
It is. And if you break that down to what we need to do every year, it means we need to be building about 5,000 miles of high-capacity transmission lines every single year.
Okay, 5,000 miles is the target. What did we actually build in 2024?
Fewer than 900.
Oof. That's not even in the same ballpark.
We're moving at less than 10% of the speed we need to be. And what's worse, back in 2013, we were building almost 4,000 miles a year. So we haven't just stalled, we've actually gone backward.
Right when we needed to be hitting the accelerator. So let's talk about the why. For decades, electricity demand was, well, it was kind of boring, wasn't it? It was flat.
Boring was good. It was predictable. Efficiency gains from things like LED bulbs canceled out all our new gadgets. But that era is officially over. Grid operators are now projecting 3% annual growth. We have not seen rates like that since the 90s.
And this isn't just people buying more gadgets. The report talks about these new demand classes.
Right. It's a perfect storm. You have three huge drivers hitting all at once. First is manufacturing reshoring, specifically the semiconductor fab.
The chip factories. We see the headlines, Intel in Ohio, TSMC in Arizona.
Exactly. But you have to understand, these aren't just big buildings. A modern chip fab is like a gigawatt-scale energy vacuum. A single one needs 100 to 200 megawatts of power, and it has to be perfectly stable.
Put that in perspective for me. 200 megawatts is.
That's enough to power a small or maybe a mid-sized city, and if that power flickers for even a millisecond, you've just ruined millions of dollars worth of silicon wafers.
Okay, so that's driver one. Number two is the so-called battery belt.
Yeah, over $120 billion invested in EV and battery factories, mostly through the Southeast and Midwest. But the real wild card, the one changing all the math, is AI.
The data centers.
The data centers. By 2028 or 2029, AI data centers are projected to add somewhere between 44 and 65 gigawatts of new demand.
That number, it's just hard to comprehend.
Think of it like this. 65 gigawatts is basically the entire generating capacity of the United Kingdom. We're adding a UK-sized load to our grid in just a few years, almost all of it for AI.
It's staggering.
Yeah.
I saw that winter peak demand projections jumped 18% in just 1 year because of this.
And it's putting this immense pressure on the regional grids. PJM in the Mid-Atlantic and ERCOT in Texas are basically sending up flares, saying they are running out of spare capacity. The phrase they used was all remnant capacity risks exhaustion.
Which sounds like very polite engineer speak for, we might have blackouts.
It is dangerously close. So you've got this huge demand, you've got the money to build. Why can't we just build? Is it all red tape? Permitting.
That's what you always hear.
And permitting is a massive problem, don't get me wrong. It takes 5 to 10 years for a single line. But the report argues that even if you fix all the paperwork tomorrow, we'd hit a hard labor wall. We just don't have the people.
The report cited almost 13,000 job openings for line workers in 2024.
And nearly 5,000 experienced workers either retired or left the industry in that same year. I mean, this is physically punishing, dangerous work. You can't just train a master technician overnight.
Which brings us to the core thesis here. If we can't get more humans fast enough, we have to change the tools. Let's start with the backbone, HVDC. Why that specific technology?
So our grid is mostly AC alternating current. It's great for local distribution, what comes out of your wall, but for moving huge amounts of power over, say, 1,000 miles from a wind farm in Iowa to a data center in Virginia, AC is pretty inefficient.
It's like taking the back roads instead of the interstate.
That is the perfect analogy. HVDC is the interstate highway system for electrons. It loses only about 3% of its power over 1,000 kilometers. For AC, it's more like 6 or 7%.
That doesn't sound like a huge difference, but I guess at this scale.
At this scale, that 3% difference is enough energy to power a whole city. It's massive. And there's another advantage: control.
What do you mean by control?
In an AC grid, power just flows along the path of least resistance. You can't really steer it. With HVDC, you can. It's like having a dedicated express lane on the highway where you control exactly how much traffic goes through it and where it goes.
And it has a smaller footprint, physically.
Yes. Fewer wires, narrower rights of way, which helps a little with the permitting and landowner issues. The big vision here is what the sources call a macrogrid, an overlay of these HVDC superhighways connecting the whole country.
And we are seeing some of these get built, right? Like the Grain Belt Express.
Yes, that's an $11 billion project that finally broke ground in 2026. It's a huge line carrying wind power from Kansas eastward. There's also the Trans-West Express connecting Wyoming wind to the West Coast.
Okay, so HVDC is the answer, but we hit that same wall again. The supply chain for all this specialized equipment is a total mess.
It's incredibly fragile. The wait time for the converters and transformers you need for an HVDC station is 2 to 4 years right now. And get this, 80% of our large power transformers are imported.
And what about the actual cables?
There are zero. No major U.S. headquartered manufacturers of HVDC cable. We're totally reliant on Europe and Asia, and their order books are full.
So we need a grid to support U.S. manufacturing, but we don't have the U.S. manufacturing to build the grid.
That's the trap, and that's where the robots come in. This is the force multiplier.
I love this idea, and the report is very clear. This is not about robots replacing workers.
No, because there aren't enough workers to replace. The labor shortage is just too deep. This is about augmentation. The math they use is that one line worker supervising a robotic system can do the work of 5 to 10 people.
That's how you get from 900 miles a year to 5,000.
So let's start in factory. How do robots help reshore the supply chain?
It's about offsetting labor costs. If you want to make HVDC cables here, you automate the process.
Are there real examples of this happening?
There are. A company in Michigan, TS Conductor, got Department of Energy funding for a highly automated factory. And Prysmian is expanding in Pennsylvania using something called robotic extrusion.
Robotic extrusion, what does that do?
It gives you incredible precision and consistency. You can run the factory 24/7 with a defect rate of less than 1.1%. With manual production, it's more like 1 to 3%.
That seems like a small difference. 1% versus 0.1%. It sounds small, but if you're burying that cable for 50 years, a single microscopic flaw can cause a catastrophic failure. You need perfection. Robots deliver that.
Okay, so robots help make the parts here. But the part that really blew my mind was the robots out in the field. Let's start with inspection, what the report calls the low-hanging fruit.
This is tech that's basically ready to go. You have these robots like the Flex Rover or the Line Scout that literally crawl along the power lines.
Wait, on live wires?
Yes.
With the power on?
Yeah, that's the game changer. Normally, you'd have to shut the power off to do a close inspection. These things just crawl along, looking for damage, while the electricity is still flowing.
The time savings must be enormous.
It cuts inspection times by 50 to 70%. Drones are doing it too, using AI to spot tiny cracks a human eye would miss.
So inspection is one thing, but construction is the real bottleneck. This is what the report calls the construction frontier.
This is where the true acceleration happens. Let's talk about autonomous trenchers.
Robotic.
Pretty much. They're adapting technology from offshore wind ships, which have to lay cable on the seabed with no one around. These are guided plows using GPS to lay underground cable with centimeter-level accuracy.
So no more massive crews with shovels and backhoes.
Exactly. And they can run around the clock. They don't take breaks. They just dig. This is huge because a lot of these new HVDC lines will probably have to be buried to get them approved.
What about building the towers? That feels like it needs a human touch.
You still need humans, but you can give those humans superpowers. The report talks a lot about exoskeletons.
Powered suits.
It's not quite Iron Man, but it's close. These suits help workers lift heavy cables and equipment, which reduces fatigue and injury. It means older, experienced workers can stay on the job longer.
And they have robots tightening the bolts.
Robotic bolt tightening. It sounds trivial, but a big tower has thousands of bolts. A robot makes sure every single one is perfect. Then for the really big pieces, like the converter modules, you're using autonomous cranes.
The whole process just changes. It's not one step after another. It's all happening in parallel.
And it starts before anyone even touches the dirt. They build a digital twin first.
A virtual model of the whole project.
Exactly. They use AI to map everything perfectly, and they run simulations to find problems, a rock formation, a tricky angle, and solve them in the computer before the real robots even show up.
The return on investment for this sounds, off the charts. The report mentioned a benefit-cost ratio of more than 10 to 1.
At the system level, yes, the robots are expensive, sure. But if you can cut construction time in half, you're saving billions in the long run.
So we have the tech, we have the need. But there's another layer here that makes it all even more urgent, and that's national security.
This is the angle that gets lost in the debate sometimes. The grid is defense infrastructure.
Because our military bases run on it.
They get more than 99% of their power from the civilian grid. If the grid goes down, our bases go dark. But it's even deeper than that.
It goes back to that supply chain vulnerability.
A huge risk. If 80% of your critical transformers are made overseas, what happens in a trade war? Or an actual conflict?
We'd be completely stuck. Can't replace a critical part.
We would be incredibly vulnerable. And that's why we saw that White House executive order in February of this year, framing grid resilience as a matter of national defense. It's about securing that supply chain.
Which brings it all together in what the report calls the virtuous cycle. I really liked how this connects all the dots.
It's the hopeful part of this whole story. It works like this. First, you use robotics to accelerate the HVDC build-out.
Step 1, build the grid fast.
Right. Step 2, that reliable grid attracts high-tech manufacturing. The chip fabs, the data centers, they want to be here because the power is stable.
Step 3, those new factories create this huge domestic market for grid components.
Exactly, which then justifies building automated U.S. factories to make those very components.
And step 4, those automated factories make the parts faster and cheaper, which helps us build the grid even faster.
It becomes a self-reinforcing loop, and suddenly the U.S. isn't just an importer of this technology, we're exporting the solution.
It's a really compelling vision. But we have to come back to that reality check from the beginning. We're at 900 miles a year. We need 5,000.
We are at an inflection point. The gap between what we need and what we can do is getting wider every single day.
So let's wrap this deep dive up.
Yeah.
What's the single biggest takeaway for someone listening to this?
The takeaway is that money is no longer the bottleneck. We can't just write a bigger check to fix this. The solution has to be a fundamental shift in how we build. From manual and slow to automated and fast.
Using our strength and technology to fix our weakness in infrastructure.
Exactly. Think about it. The U.S. led the world with rural electrification, with the interstate highway system. We did that with huge pools of manual labor that we just don't have anymore.
But we do have the tech.
We lead the world in AI and robotics. So the question for this decade really is, can we leverage that leadership to build the physical infrastructure that powers the AI era itself?
Or does the energy bottleneck end up choking the whole economic boom before it can even get started?
That is the question.
It really makes you think. We talk about AI in the cloud like it's all immaterial, but it lives in a physical data center that needs a physical wire connected to a physical power plant. And someone or something has to build all of it.
And right now, that something had better be a robot or we're in real trouble.